Hi everyone. First of all, thanks to the organizers and especially Taisa for putting up with a lot of my change of plans regarding this presentation. It's a shame that I cannot be there. I'm happy to be able to give this talk. Okay, so I will talk about observing relatively nearby AGB stars or fairly nearby AGB stars with ALMA and SPHERE, and about what we can see very close to these stars and what we can say about what's happening in this wind acceleration region and the dust formation and zones. So just to give a bit of context, this is a very schematic view of an AGB star. In red, we have the central star, which is pulsating and having convective streams that go up and move material up. And this forms this extended atmosphere shown in blue around the star, where dust can form and grow. And eventually, if we form enough dust, that the radiation pressure acting on these grains is enough to drive the outflow, we expect the outflow to be driven. And especially for oxygen-rich AGB stars, which are the subject of this talk, we expect these grains to grow to fairly large sizes of at least 0.3 microns. And that's because they need to have enough scattering cross-section to be able to drive these outflows. The ones that can form close enough, they have very low absorption cross-sections. So the idea is that we can then observe nearby AGB stars with ALMA and SPHERE, and we can trace the conditions of the gas using ALMA, and we can study the properties of the dust using this polarized light that is polarized by the scattering on the dust grains to then learn something about what's going on with the gas and what's going on with the dust. Just to give a little bit more context now from the modeling perspective, this is a figure from Blad et al. 2019. These are the Darwin models from the group in Uppsala. And here they have all their wind driving models in which you can see the mass loss rate in the y-axis and the expansion velocity in the x-axis. And here you can see grain sizes. So the wind driving models, they have grain sizes which are larger than 0.3 microns. And you can see the typical gas to dust ratios that they have, which are typically 1,000 or a little bit less than 1,000 up to a few thousand. So this to give a bit of context to the observations that I'm going to show you now. And the main species that we expect to see are aluminum oxides and magnesium-rich silicates, and it's fairly well accepted that in order to drive the wind, you need to have the silicates form, because otherwise the dust is just not abundant enough. Okay, so I'm going to talk about two stars only, Myra and Ardor, and I'm going to talk about some results that we published in 2018 and 2024, and then I'm going to show some new data, which I think are really cool with ALMA. So yeah, but there's not much results in the second part. It's just some new data. So I'm showing here this vibration excited CO line. So it's a line of CO. It's a rotation line of CO within the first excited vibrational state. And we see there is a dark region here. I'm going to show a few of these plots. So just to explain quickly, the black region here is where the star is. And then we see absorption from the gases around the star against the central star. And when we subtract the continuum of the star, we get negative values here. So that's why it's black. And we have the emission around the star. So this line is only excited very close to the central star. So we see a ring type of thing around the star. And then if we extract the spectrum towards the star, we get absorption, as I said. It's negative because we subtracted the continuum, and we get emission from around the star. If we integrate the spectrum over a large region. And in color, you see just the integrated line summed over all the frequencies. So what we did in this paper in 2018 was to model this vibration excited line towards Myra. And we just had a very simple model with a shell around the central star. And we were able to constrain the excitation temperature, the density, and the velocity with very simple assumptions. That reproduce fairly well the velocity profile. But what we were really after was to compare what we were getting from the gas with what we were getting from the dust, which is shown here in these sphere observations. So in the color, so Myra A, the AGB star is here, shown by the contours, the continuum. And in color, you see the polarization degree, so which is tracing where the dust is to a first approximation. And the surprising thing about Myra is that we don't see a lot of polarized light around the AGB star. For other nearby AGB stars like W Hydra and Adorados, we see polarization degrees that reach 10% or 15%. Here, it peaks roughly at 3%, which is a bit surprising. So in the end, our conclusion from this comparison was that we'd expect to see a lot more dust or a lot more polarized light for the amount of gas that we were inferring to be in these inner regions. So our conclusion is there is a lot of dust there compared to the amount of gas. These grains must be relatively small, which was kind of puzzling for what we're trying to do, explain the wind driving, in which models find that you need these 0.3 micron grains. So that was one puzzle that we got. Now I'm going to move to another star, which is Adorados. And for Adorados, luckily there were 2 programs that were observed close in time, so we ended up with more lines than expected. So I'm showing here all lines of CO and 13 CO. This one is in the ground vibrational state. These 2 in the first vibrationally excited state. The one of 13 CO is also on the ground vibrational state. There's a paper that has been recently published now. So in this case, we had a lot more data, which and we had a much more complex picture as well to explain. So here you're seeing the radial velocity model and density and temperature that we came up with based on the data. I'm not showing the comparison to the lines. If you're interested, you can go take a look at the paper. But we in the end had to give up our assumption of spherical symmetry because we just couldn't fit the line profiles with that assumption. And that's what you see in the red lines here, that some parts of the star we had to assume that we're moving in a different direction than other parts. But what I want to draw your attention to is that the temperature profile that we find is really steep. It seems that the temperature drops to about 1,000 Kelvin already within like 1.6 times the submillimeter stellar radius, which is very steep. So our model basically consists of one shell where the density is very high, of the order of 10 to the 17, or well, I say 10 to the 11 particles per centimeter cube. And this shell contains 3 times 10 to the minus 5 solar masses of gas, more or less. And this is much larger than the amount of mass that our door loses per year, which is of the order of 10 to the minus 7 solar masses. So the conclusion then is obviously that most of this mass doesn't leave the star in a pulsation cycle, but it falls back and it stays there for hundreds or even 1,000 years before being ejected. So this it's kind of a stationary or a very dynamic but gravitationally bound shell to the star. And then at about 1.6 stellar radii, again, the limits here are a bit, there's a bit of uncertainty, but still very close to the star. Our model is already consistent with this, what we would expect from extrapolating from the outer outflow. So what is known from this very large extent emission in CO. If you extrapolate this mass loss rate in, these are more or less the densities that we expect to find in here. So it's already, what it means is that this model is consistent with the outflow starting at 2 stellar radii or 1.6 stellar radii, somewhere very close to the star, although we cannot be sure that that's indeed the case. So then I'm going to talk a little bit about the sphere observations towards Adorados, which probe again the dust. And so these are 3 wavelengths that we have here. And the radius of the star invisible is very similar to the radius that we see in the submillimeter, even though the radiative processes, the sources of opacity in these 2 regimes are very different. we have molecules and dust scattering acting in visible wavelengths and free emission acting the submillimeter. But these two radii are very similar. They are more or less 1.25 times the radius of the sun in the infrared, which is the wavelength that the star looks the smallest. And this is how the polarized light looks, the polarization degree looks towards the star. As I told you before, we see this much larger polarization degree of the order 10%, which is very different from what we see for Mira. And one thing that I think is interesting to point out when I was preparing the talk, I was thinking, is that we see dust basically at the visible photosphere. We cannot make the inner radius of the dust envelope much larger than the visible photosphere. So at 1.25, the infrared radius, there seems to be dust already there, which I think is very interesting. And yeah, it's something that I thought was good to mention. But then we're still working on this model. This is a paper that is in preparation now, but we have been trying to turn this dust model around in all the way that we can to make it work and to see all the assumptions that we are making, trying to see what type of changes we can make to get more dust or dust that has more cross-section to drive the wind. So we find dust to gas ratios that are within the expected range, like 4,000 is in the high end of the interval, but still more or less within the expected range, especially given the uncertainties. But the grains seem to be too small, and is only a factor of 2 small, but this makes a huge difference for the cross-section. And it also has a huge impact on the spectral dependency of the scattering. So it's very hard to make the grains larger and make them fit this how the polarization degree varies with wavelength. So this means that it doesn't seem that the wind is viable for what we know for this star as well, which is puzzling again. So the conclusion from these two things at the moment is, when we look at them in detail, we find the right elements, but when we try to work out if the numbers that we measure match, it seems like we're missing something. And of course, we're trying to look more into it and learn what something might be. So now I'm going to change gears quickly for the last couple minutes and show some new ALMA data.
You have 3 minutes.
Which I think is really, yeah, thanks. So first, I'm going to talk again about the 2 stars. And we observe 5 stars actually in this second phase of this study, but I'm just going to show the same 2, not to make it too complicated. So this is Mira, seen at 340 gigahertz, and you see that the first thing that is interesting at the star, it's not symmetric. We see there's more emission coming from this bottom part here. And I'm going to show again this vibrationally excited CO line. And so we see an emission from around the star and an absorption towards the star. And what is really cool is that we have such high resolution compared to the size of the stellar disk that we can take spectra from different parts towards different parts of the stellar disk, and we see how this velocity pattern changes as when we move across the stellar disk. So we can really understand how this gas is moving this extended atmosphere. I'm not going to give you results. I'm just going to give you this very low-level examples of the things that we are looking to do now. And with Far Dorados, which is the biggest star on the sky, with the exception of the sun, of course, is we can have so much resolution compared to the stellar disk. So here you're seeing again the continuum of the star in the submillimeter compared to the resolution that we have, that we see this convection pattern and the bubbling photosphere of the star. This is a paper that was recently submitted, and you're going to be able to see it soon. But we can see even how the stellar disk warps and how we see all the structure on the edge and against the star, which is extremely interesting. And so again, I'm going to show now, sorry, there was no poster. You're going to see now the 2 lines of SIO, one in the V equals 6 level. It's a rotational transition within this level again, which, as you can see, is only excited very close to the star. Again, you see the continuum in the color, and you see it in absorption against the continuum here. And you see that the absorption is not uniform, so the distribution of the gas or the excitation of the gas is not uniform in this very thin layer around the star. And we can do the same thing. We can look at different parts and see how the velocity of the gas changes as we move across a stellar disk. And what I'm looking forward to doing now is some sort of tomography of this extended atmosphere. For instance, by looking at lines with different excitations as lines in the V equals 2 and V equals 6 of SIO. As you can see, they probe different extents of these extended atmospheres and look at how the velocity profile changes, not only across different regions of the stellar disk, but also different depths of the stellar disk. So I think we'll learn a lot about what's going on in this extended atmosphere in the coming years. And yeah, I'll leave you with my summary because I think I already am out of time. Thanks.
Hello, thank you for a great talk. I have two questions. The first of which I didn't quite follow, apologies if I missed it. How did you fit to the grain sizes? What models did you use to do that?
Yeah, so I'll go back here. So we are using RADMC3D as a code for modeling the radiative transfer around the star, and we use another code for calculating the opacities based on the grain model that we have, which now is just spherical grains, and then we assume a single grain size, and we are exploring different grain species, but we are calculating the opacities from the optical constants, both using me and distribution of hollow spheres, which are two different types of grain models. And yeah, so then we calculate the grain model, we calculate the opacities using this grain model, and then we put this into RADMC3D, and we do this radiative transfer basically in 3D, which takes into account the direction of scattering and everything. And then, yeah, we make the images and compare to the data.
Fantastic, thanks.
Answered your question.
No, that does, thank you. And my second question was, have you thought about how polarized these atmospheres might be, like the molecular part of the atmosphere?
Yeah, so this is something that I have thought about, but I haven't really tried to calculate yet. But from talking to people, what I have heard is that you don't expect a lot of polarization from molecules alone, like of the order maybe of a few percent. But yeah, it's something that we would have to take into account. But if molecules are producing a significant amount of polarized light, that would only make our problem worse, because now we seem to be lacking dust, and yeah, but that's something that I would like to know more about, but I haven't really managed.
Okay, thank you.
Hello, fantastic results. I am puzzled by the fact that in your observations of Mira and Erdor, you don't observe really a radio photosphere. I mean, you can really observe the star. I mean, the continuum you observe at this wavelength is the continuum of the star, or you observe something more extended than the star itself. You can really go down to the photosphere.
No,
Because
no,
in the case of, sorry, yeah.
No, it is indeed some kind of submillimeter photosphere. So the star would look the smallest in the infrared, and as we move to the radio or sub of the millimeter, the star would progressively grow as you move to lower frequencies, because the free opacity is increasing with decreasing frequency. So the star will look bigger to the smaller the frequency you move. So now we are seeing in the submillimeter, we are seeing something in between what you would see in the radio and what you would see in the infrared. So you can also probe the physics of what's happening there, or the gas properties, by looking at different frequencies just at the continuum, and then you can make also some kind of tomography of this extended atmosphere.
Okay, thanks.
I have a quick question. The Myra result was interesting. Maybe there's too little dust, but it looked like it had a morphology. On your longest wavelength polarized picture, looked like there were two, I mean, it's low signal, but it looked like it had two lobes. And also the central block was not coincidental with your position of the star, but that's interesting too. Was that did it ever come up in your analysis? Did you see it?
Definitely
am I
did.
dreaming?
So no, it definitely did. And what is really interesting that we see these two blobes in gas as well. And the dust seems to be tracing the edges of the two blobs that we see in the gas. So I advise you to take a look at the paper if you're interested, because it's really puzzling. But it doesn't seem that the dust is driving the gas, but it seems to be mostly trapped at the edges of these lobes that we see in the gas as well. So I'm very confused about what's going on with Myra. But yeah,
the triple.
There seems to be a lot of things happening.
Well, since we know it's a binary, then maybe there's a third star.
Yeah, some people have proposed, but no one has found any direct evidence yet. Yeah.